All right, welcome back to Introduction to Machine Learning. I'm Sundeep Rangan at New York University. This is our 10th unit on convolutional and deep neural networks. These networks, of course, have been all the rage in machine learning and what's created all the interest in this field in the last 5 or 10 years. And is possibly why you were taking this class yourselves. Before I go on, I want to thank two of my colleagues who helped prepare these slides, Professor Yao Wang at New York University and a great Professor Phil Schneider at Ohio State. So, if you manage to get through all these sections in this unit, what I'm hoping to teach you is following. First, just to explain qualitatively what the motivation for deep networks are, and this will get us into a very important concept called feature hierarchies. Then I'm going to go more into the mathematics of a particular type of layer called convolutional layers, and I hope you'll be able to work out the math for these. You'll be able to then implement these convolutional layers in TensorFlow, as well as describing and implementing various algorithmic enhancements such as dropout, batch normalization, and so on. We're also going to learn about what is a GPU and know when to use it, and finally try to describe and implement an important idea called transfer learning. So let's just start with a little bit of the history that created deep neural networks. So deep neural networks really started in the field of image classification. And if you looked at image recognition systems that researchers were looking at, say about pre-2009, about a little more than 10 years ago, they were all being validated on relatively small data sets. So for example, in the earlier units, you looked at the MNIST classic data set on digits, and it's small in a number of different ways. It has a small number of classes, or 10 digits, relatively small number of examples, about 70,000 between training and test, and they're also low resolution. There was an interest in looking at a little bit higher resolution, more complex data sets, but they were still relatively simple. For example, the CIFAR data set, which we'll talk about later, had about 10 classes. It's a little more complicated because it's color and a little higher resolution, but it was still relatively small in all three of these dimensions. Same, they tried to get a little bit harder with the CIFAR 100, and then there's the Pascal VOC. And one result of working on these relatively small data sets was that the performance had kind of saturated, and it was really difficult to make any significant advances. In 2009, a very important new data set was created called ImageNet, which was really fundamental to creating the whole deep learning revolution. And the concept here is that better algorithms really needed better data. Now that's actually very counterintuitive, because you would think that if researchers were struggling with much smaller data sets, it would actually be futile to start looking at even more complicated data sets. But it turned out that only by looking at much more complex and rich data sets, you could figure out the structure that would be needed to handle or advance machine learning algorithms. So the ImageNet dataset, some of the images are shown here. And the goal was really to try to create kind of as quoted in the paper, to map out the entire world of objects. Well, of course, it's not the entire world of objects, but it's a vast number more images than any previous dataset, about 3.2 million images in the first release of this. Now, that's an enormous undertaking to get those images, but also remember, for supervised learning, you have to label each of these images. And in this great article, they talk about some of this struggles that they had with this. And one of the final solutions they came up was an automated way called Amazon Mechanical Turk. Now, just to give you an idea of how complicated this data set is, it has hierarchies of categories. For example, here, there's a whole category just on geological formations. And then it has various subgroups within that. This came out in this paper in 2009. At the time, it wasn't realized its influence that it would have. But this paper by Fei-Fei Li, who's now at Stanford, would really be the kind of impetus for a lot of the research, and I'll show you going on. So after creating this ImageNet dataset, in the next year, they created what's called the ImageNet Large-Scale Visual Recognition Challenge, and it would be held yearly starting in 2010. This was an enormously much more challenging recognition task than any previous image classification problem. Well, first of all, there were many more classes. There were about 1,000 of them. And in each image, there was not a single class, but you could see many different objects that would have to be detected. For example, a person, a hammer, a flower pot, and a drill in this case. There's also, as I said, very fine-grained classifications. For example, there are 120 categories just of dogs. And the objects weren't nicely just cropped out and centered. They could be in various positions in the images, in various scales, rotations, lighting. They could be occluded and so on. So there had been really no data set this difficult that was people were previously even attempting. So the first 2 years of the challenge, networks kind of saturated about maybe low 70s of accuracy. And these were very good algorithms. But suddenly in 2012, there was this stunning breakthrough from a new set of algorithms that leapfrogged in performance, maybe going from the low 70s or mid 70s all the way up into about like 80, 83% or so. This network that did this was really what's now recognized as the first deep network. The network was later coined AlexNet, named after one of the authors of the paper, and it had an accuracy or an error rate of about 15%, or what's called the top 5 error rate, meaning that you get the class within the top 5 in this case. And this was an enormously stunning breakthrough. All these researching teams had been struggling to break this around 75% barrier, and suddenly it had jumped out with this almost quantum leap in performance. And soon, really, all the remaining competitive networks would be deep networks in the subsequent years, and the performance would improve more. The paper that ended up to coin this network would go on to be really one of the key initial papers in deep neural networks, and we'll talk about this network as we walk through this class. The network was called AlexNet after the author, and the key idea is to build a very deep network. What we mean by deep is having many layers. In this case, there were 5 what are called convolutional layers, and I'll talk about what that means in this unit, plus 3 fully connected layers at the end, which are, so for a total of 8 layers. The number of parameters in this network is vastly more than any other network that had been previously done, with about 60 million of these parameters. Because it's a classification problem, the final network is 1,000-way softmax, because you have 1,000 classes. This idea had never really been attempted before. Okay, so let me qualitatively describe why you might think that deep neural networks would be able to achieve the performance they did, and that will lead me to an important concept called feature hierarchies. So let's start by looking at what you might call a one-layer neural network, or really just a linear classifier. So suppose I have data, which looks like this. So I have a bunch of green dots and orange dots, and I want to classify them or separate them. In this case, they're very linearly separable. So I could just use a standard linear classifier. So I would take a linear combination of the data and then maybe pass it through, say, a logistic function to get the probability. You can think of that like just a single layer neural network, where this is a single output, because it has a linear combination and then an activation function. Now, in this particular case, this unit in this neural network would be, of course, dividing that space into 2 simple linear half spaces. For example, here, the blue and the orange space, and these are just linearly separated. And what we can say then is that this simple output is, we'll say that an output is tuned to an input x whenever its output is largest. And in this case, that will be corresponding to one of the two half spaces. And why is that the case? Well, if this is a sigmoidal activation, this output is large whenever the input to that activation is large. But that input is just a linear combination of the inner product of the input with the weights, and that will be largest when that input is linearly aligned with that weight. Well, what if I wanted to get a more complex shape? So we looked at this exactly actually in the previous unit. Suppose here it's not linearly separable. There's some data points in the middle in this kind of circular region, and then I have a ring of data points around that. Obviously, this is not separable with any simple linear classifier. This is exactly the example I gave at the beginning of the neural network lecture. But as I described there, what you could do is you can use 2 layers instead of 1 layer. In the first layer, you get outputs which classify the region into linear half spaces, but then you can go and combine those half spaces to get more complicated shapes. And as I combine those shapes, I can actually construct this more complicated non-linear region here. But what do I do then if I get an even more complicated shape, like this spiral, where I have a ring of blue dots and another ring of orange dots? Presumably with enough of those shapes, I could probably split this out, but I would need a large number of linear lines to try to separate out these shapes. Instead of trying to create many more linear regions with a single layer, I could use multiple layers. So for example here, in the first layer, I divide this into linear half spaces like this. So you can see here it's getting the bottom right, the top right, and so on. But then when I make linear combinations, I can get more complicated shapes. For example, this neuron seems to be sensitive here to the center dot, this kind of to a circular region on the top right, this to kind of a triangular region on the center right, and so on. And when I combine these, I can get even more complicated shapes here, like the beginning of this arm of this spiral. And when I combine all of these, I can actually construct this very complicated shape tracing out this spiral here. This is actually an output of a real trained network, which comes from the output you can actually visualize in TensorFlow with a tool called TensorBoard, which I won't go into in this unit, but you can read a lot about it in the web. But what do I do if I have an even more complicated problem? Like I want to detect from an image if it's a cat. This is not an obviously simple 2-dimensional case like I just showed you before. The idea here then is to then build a very deep neural network. A network with many, many layers that take the image at the beginning and build one layer at a time. As you progress, you get more and more complicated features as you progress to the end. This concept is called feature hierarchies because simple features build to more complicated features and can eventually get higher semantic level understanding of what's in an image. And this is in essence the power of deep neural networks. Now, there's actually kind of a biological inspiration for networks or deep neural networks, because they at least at some very high level, mimic the way the brain processes visual information. So, for example, if you were to see a cat through your eyes, it will be recorded in your eyes, of course, and then sent to the optic nerve to the part in the brain called the visual V1 region, which is at the back of the brain. And that will typically, or what's believed, to extract very low-level features of the image, things like detections of edges, curves, and so on. But as you progress through the brain into the subsequent brain regions like V2 and V4 and so on, neurologists believe that more high-level semantic information is being decoded, and that's where we can understand the nature of objects, for example, if it's a cat. Now, a question then, this idea of feature hierarchies, and deep neural networks, why have they really become all the rage in the last 10 years? So actually, there's a very good article which sort of describes the history. And one thing to understand is that actually the idea of using multiple layers is not particularly new. It at least dates back to the mid 60s. And some of the key layers, such as convolutional layers and pooling that I'll talk about, were known also back in the 80s. But at that period, using very long networks was very challenging. One of the key issues is that when you build a very large network, you have a large number of parameters, and you need therefore, a large amount of training data. And this is where that ImageNet classification problem came in. It was really the first large data set that you could have that could suitably train these very large networks. There were two other issues. The second was the limits of computational power. When you want to train a network with millions of parameters, you need very specialized hardware to do this, and we'll talk about some of those advances later on. And there were other more technical reasons. One of them is called, for example, the vanishing gradient problem that I'll also talk about as we go through this. AlexNet really introduced some key solutions to this. Most importantly, though, it was really being trained on the first large data set, which enabled to train millions of parameters. But it also had some other smaller feature advancements that drop out certain activations. And I'll talk about some of these tricks as we go through the unit. Okay, so that wraps up our little bit of history and motivation. And in the next section, we're going to move on to talking about one of the key concepts, which is convolutions.